So this is another filter, a second order filter. Could be a band pass, could be a band reject or band stop. What we have to do in this problem is to find the transfer function of the filter, and then we are going to plot the magnitude response of the filter. And we will decide what type of filter is this. It's going to be either a band stop filter or a band pass filter. So let's go ahead and figure out what is the transfer function, that is V out over V in. So let's go ahead and first write down the transfer function in terms of voltage division. So output in terms of voltage division, remember in phasor domain, this will be XL and this will be XC. So output, which will be a function of j omega, will be equal to, if we call the combination, parallel combination of XL and XC as Z, then this will be simply R over R plus Z times Vn. And the transfer function AH of j omega will be equal to output over input, which will be R over R plus Z. Now Z is the parallel combination of where Z is equal to XL parallel to XC, which we can write as 1 over XL plus 1 over XC, 1 over j omega L plus 1 over XC is 1 over j omega C. So 1 divided by 1 over j omega C is simply going to become j omega C. And if I simplify it further, then Z will be equal to j omega L times j omega C will be j square, which is -1 omega square LC. And then j omega L is going to go in the numerator. So j omega L divided by 1 minus omega square L times C. That is my Z. Therefore, my H of j omega can be written as R over R plus j omega L over 1 minus omega square LC. Let's simplify this. 1 minus omega square LC is going to be multiplied by R, and this is going to go in the numerator. So R times 1 minus omega square LC divided by R times 1 minus omega square LC plus j omega L. So this is my transfer function. As you can see, the numerator is real and the denominator is a complex number. So I can leave it as my transfer function, or I can multiply it by R and then write it down in terms of R minus omega square RLC, and the denominator will be R minus omega square RLC plus j omega L. It doesn't really matter which way you want to write it. But this is your transfer function, which is basically the answer of the first part. Now, this transfer function, of course, there's a magnitude response associated with it, and there's a phase response as well. We can go ahead and write the magnitude and phase response expressions as well. So the magnitude response equation is simply going to be R1 minus omega square LC divided by the square root of R square 1 minus omega square LC square plus omega L square. That is the magnitude response expression, and likewise the phase response expression is going to be the phase of the numerator, which is, since it's a real number, it's going to be 0, minus the phase of the denominator, which will be R10 of imaginary number, which is omega L, over real number, which is R1 minus omega square LC. So negative arc10 of omega L over R minus R times 1 minus omega square LC. That is going to be the phase response expression for this transfer function. So that is, I believe, our part number 1, derive the transfer function of the following filter. Again, we do not know what type of filter is that. We're going to go ahead and plot the response, although you can kind of, figure out what type of filter is this by looking at when the inductor is like at low frequencies, inductor is going to be acting as a short circuit. Let's say a DC is going to be short circuit, capacitor will be open circuit, and output will be equal to the input. And at very high frequencies, capacitor is going to be acting as a short circuit, and inductor will be acting as an open circuit, j omega L and 1 over j omega C. And then again, input will be equal to output. So we know that it is either a band stop filter or a band pass filter because you have the output. Actually, it's not a band pass filter because you have the output at low frequencies, you have the output at high frequencies. That means it has to be a band stop filter. At certain frequencies, your L and C are just going to become open circuit when they start exchanging energy between them. At that time, XL and XC are just going to become equal, and they are going to cancel each other, making the equivalent impedance to be equal to infinity. So it's going to act as an open circuit. Admittance is going to become 0, and impedance is going to become infinity or open circuit. And at that time, you won't have any output. So this is a band stop filter. It's not a band pass filter. And that we can prove, of course, if we plot the magnitude response of the filter. So let's go ahead and plot the magnitude response of the filter. Let's go ahead and open MATLAB or Octave. And let me move this here. My Octave on top. So let's go ahead and we can plot it in terms of omega or f, whichever way you want. Let's go ahead and plot in terms of omega because we just want to see the response anyways. So let's go ahead. We started 10, and then let's see what values are given in the second one. R is equal to 100. I'm going to take those values. So omega, I'm going to go ahead and define from 10 and 10 and 1 exponent 6, let's say. And then I have R is equal to 100. And L is equal to 2.2 exponent negative 3. And C is equal to 220 exponent negative 9. And then I'm going to go ahead and write down my transfer function quickly. So my transfer function is H is equal to R times 1 minus omega square else RC omega square times R times C. And there has to be a multiplication sign here, divided by R times 1 minus R times 1 minus omega square LC, omega square times L times C. And numerator is also LC, not RC, L times C. And plus I times omega times L. Okay. Let me see if parentheses are balanced. Looks like they're balanced, so looks good to me. Let's go ahead and evaluate that. And then magnitude of H is simply the absolute value of H. And then I'm going to plot sin of X, omega, and magnitude of H. And X label is radian per second, which is omega. And my y label is the magnitude of h of j omega. So let's go and plot this. And as you can see, this is turning out to be a bandstop filter as we expected. So this is the bandstop filter. So quite easy to do the derivation as well as plotting. We have done plotting several times. Plotting doesn't change. So this is a bandstop filter. It's also called band reject. And that's how you're going to do the derivation of the transfer function as well as plotting of the magnitude response.